Good day, my name is Tuvihle Spanda. Welcome to my second presentation on Fluid Mechanics 101. So recap on the Coulomb-Pourquoi equation. If the flow is turbulent, that is if your Reynolds number is greater than 4,000, calculation of the friction factor is not straightforward as that for the laminar flow. If you remember from my last presentation, when the flow is laminar, our friction factor we calculated by dividing 64 by the Reynolds number, then you get your friction factor. In turbulent flow, the calculation of friction factor F is more complex. The friction factor depends on the pipe inside diameter, the pipe roughness, and the Reynolds number. Based on the work by Moody, Coulomb-Pourquoi, and others, the following empirical equation, which means it was derived from experiments, known as the Coulomb-Pourquoi equation, has been proposed for calculating the friction factor in turbulent flow. So this is the Coulomb-Pourquoi equation. So your F is the Darcy friction factor, which we'll use in the Darcy's equation, same as we used in the last presentation, and it is dimensionless. Then D is the pipe inside diameter. You should take note that usually diameter, they give you the outer diameter. So you need to derive the inner diameter from the thickness of the pipe. Then E is your absolute pipe roughness. This usually get it from the tables. Then R is your Reynolds number, which is also dimensionless. The ratio ED is known as the relative pipe roughness and is dimensionless since both pipe absolute roughness E and pipe inside diameters are expressed in the same units, which means the units cancel each other. So pipe roughness table. So these are the pipe roughness, usually get it from the tables. For example, if you know Paris Chemical Engineering Handbook, you can find this one. So the absolute pipe roughness depends on the internal condition of the pipe. What does it mean? Sometimes the pipe roughness is different for a new pipe versus the one which is scaled. Generally, a value of 0.002 inches or 0.05 millimeters is used in most calculations, unless better data are available, which means if you don't have a better data, for example, from this table, or if it's in a range like this, you can just use the 0.02 inch or 0.05 millimeters, unless, of course, you've been working with such pipe material for a long time and you know a specific figure. Coulomb-Pourquoi equation. It can be seen from the Coulomb-Pourquoi equation that the calculation of the friction factor is not straightforward since it appears in both sides of the equation. As you can see, you have your friction factor on both sides of the equation. So you need to use numerical analysis for you to be able to solve for that F. So successive iteration or a trial and error approach is used to solve for the friction factor. An iteration is stopped when the current iteration is equal to the previous iteration. So what does it mean? It means you guess the value of your F and put it here and solve it. Then you get a figure of F on the left hand side. Then put that value of F and solve again equation till your answers do not change. Then you know you've reached the solution. So I will illustrate this by using an example. So we have water flows through a 16-inch pipeline of 0.375 inch wall thickness at 3,000 gal per minute. Assuming a pulp roughness of 0.002 inch, calculate the friction factor and head loss due to friction in 1,000 feet of pipe length. So now the solution, first of all, we are given the volumetric flow rate, which is that one. So you want to convert that to velocity. So we use the formula Q equals to VA. Then our area we know is equals to pi r squared. Therefore, our view, it's a volumetric flow rate divided by pi r squared. You want to change our volumetric flow rate from gallons per minute to cubic feet per second. So if you do a calculation, that's what you get. Then we are given the sorry, I made a mistake here. So it was meant to be, we are given the outer diameter. So it should be outer diameter is equal to, sorry. Inner diameter is equals to outer diameter minus 2 times thickness. So we are given the outer diameter. So you have to determine the inner diameter because that's where the water is flowing. So which is 16 inches, which is our outer diameter, minus 2 by 0.35 inches, which is our wall thickness. Then we get that our inner diameter is 15.25 inch. Convert that to feet, you get 1.271 feet. Therefore, our radius is 0.636. Just we get it by dividing the inner diameter by 2. Then you get your 0.636 feet. We proceed to calculate our velocity, so which means we divide our volumetric flow rate in feet by pi r squared. We get that it's 5.27 feet per second, which is same as 1.61 meters per second, and that's acceptable. On my next presentation, I will talk about what the acceptable values of your velocity, because you need certain velocity in your pipe, because if it's too much, then you get corrosion of your pipes. And if it's so on that, if it's too less, you get the laminar flow regime. And in industry, we need turbulent flow regime. So if you remember, on my last presentation, I spoke about the Reynolds number, but I didn't show how it's calculated. So the Reynolds number is a dimensionless parameter of flow. It depends on the pipe size, the flow rate, liquid viscosity, whether you put water, oil, and density. It is calculated from the following equation. Reynolds number is equal to 3162.5 volumetric flow rate divided by your inside diameter of pipe and the kinematic viscosity in centistokes. So going back to example, assume water has a viscosity of 1 centistoke. So this is the at room temperature. The viscosity of water, it's 1 centistokes. So calculating the Reynolds number from this formula now is equals to 3162.5 by volumetric flow rate of 3,000 gallons per minute divided by pipe inside diameter in inches by our viscosity of 1 centistokes. We get 622,131, which is greater than 4,000. Therefore, our flow regime is in the turbulent regime. Thus, the flow is turbulent, and we can use the Kolb-White equation to calculate the friction factor. So now we can go back to our Kolb equation to try to calculate the friction factor. So the equation must be solved for F by trial and error. First, assume that F is equals to 0.02. Usual value for this flow regime, it's around there. So obviously you want to start your first guesstimate or estimate at 0.02 so that you reach your solution first. Otherwise, if you start from your value, which is too huge, you do many iterations before you reach a solution. And you have to take a note that you can use some software to calculate this. And on my next presentation, I'll do one example whereby I'll use the software to calculate this value, and it's just one click, you're done. So, which means our first case, we said you put 0.02, you calculate it, you get this. Actually, there's a mistake here. If you put that, then you get 0.0144, right? And I put that 0.144 here, not 45. It's a slight mistake. Then my answer is 0.0144, which means it wouldn't have changed. So I know that I've reached my final solution. You can try it yourself and see what I'm talking about. Thus, the friction factor is 0.0144. You see, it's tedious. It's a bit tedious in the turbulent flow regime to calculate for the friction factor as compared from my previous presentation where for the laminar flow regime, it was straightforward. So the mode diagram can be used instead, and I will discuss this on my next presentation. So the hair loss due to friction can now be calculated using the Darcy's equation. Recap, this is our Darcy's equation, where H is the frictional pressure loss, which is the loss in pressure as the fluid is flowing along a pipe. F is the Darcy friction factor, dimensionless, which you just got now, which is 0.0144. L is the pipe length in feet. I think we're told to calculate per 1,000 feet. D is the inside pipe diameter in feet. V is the average flow velocity in feet per second. Then G is the acceleration due to gravity, which is a constant with these figures and units. So, putting back, we know our F. We put our length. We're told to calculate per 1,000 feet, per 1,000 feet of pipe length. Then our diameter, we got it as 1.271 feet multiplied by our velocity squared, which is our velocity squared. Sorry, then divide by 2g. Then if you do your mathematical calculation, there you get that is equal to 4.9 feet of head of water. But because I think in meters, that's why I converted to meters, which is equivalent to 1.49 meters of head of water. But if you remember now, this is we're given a head in meters of head of water, but we want to calculate in terms of pressure drop. But we know that P is equals to rho GH, which is density by acceleration due to gravity by our head. Density of water is 1,000 kg per cubic meter. Then G is 9.81 meters per second squared by the H we calculated on top. We get this 14,616.9 kg per meter second squared, which is equivalent to Pascal. Converting to PSI, we get 2.21. Therefore, pressure drop due to friction is 2.12 PSI. It means if I put a gauge here, then 1,000 downstream of my pipe, my pressure will drop by 2.12 PSI, which means the reading on the 1,000 feet mark will reach 2.12 PSI less. And as we go with the presentations, I will show you why we do calculate this pressure drop especially now when we start designing the pump, sizing the pump. And thank you for watching. If you have any queries, additions, subtractions, contact me on my email address. It's tubasmount@gmail.com. Please like, comment, and subscribe to my YouTube channel to learn little engineering stuff. See ya.